Hello. In this tutorial, we will look at the constraint Monte Carlo algorithm in Vampire and in particular on how to use it to calculate and extract the anisotropy energy and its temperature dependence. Why do we want to look at the anisotropy? Well, there might be a few reasons. For applications, as we can see here, anisotropy is extremely relevant. For example, for the storage technology, our hard drives, they're all magnetic devices, and the anisotropy, high anisotropy, is what allows to store the information for a long time. And for example, new memory devices such as the MRAMs, magnetic resistive access memories, random access memories, use as well high anisotropy materials for the same reason. Um, but for example, electric motors, um, as for example Toyota develops them, um, use magnetic materials. They use permanent magnets which have a very high anisotropy as well, and as well in medical applications such as for example hypothermia, or they can be used magnetic nanoparticles for treatment, for example, of cancer. And the anisotropy plays a very important role how you can use them in these cases. But it can also interesting on a more theoretical point of view to understand uh, material properties, for example, surface effects and other properties, especially anywhere related to the new technologies where we want to scale device down to the nanoscale or smaller, and there all these particular features will emerge. So it's very important to characterize them, and having an approach that allows you um, to obtain them can be very useful, especially because theories that may have been developed for bulk systems um, might not lead to or might not be able to provide um, the informations in these cases. Okay, so but why constraint Monte Carlo algorithm? Why this different approach? Well, as also said in the introductory tutorial, Monte Carlo approaches can be very useful when we want to obtain equilibrium properties because um, minimize the energy, and so will be quite efficient uh, to yield the equilibrium state. So you can obtain the Curie temperature, for example, or you can use it to obtain the temperature dependence of the magnetization, or for example, the same for the susceptibility. On the other hand, though, when we talk about anisotropy energy, what we referring to is the difference in energy between states where magnetization is oriented along different directions. And if you are in a proper equilibrium, thermal equilibrium, then the magnetization will align along the low energy state, and so we cannot obtain in such a case uh, this difference in energy. So the idea was to actually keep the system globally out of equilibrium, and while at the same time allowing the macroscopically the spin system to actually achieve the thermal equilibrium. And how is this done? So in this constraint Monte Carlo algorithm, where constraint is the main idea, we add an extra degree freedom. So we use two spins in the algorithm rather than one, and we use this to constrain the direction of the magnetization of the global magnetization of the system along a specific direction. Because then the system is not in the equilibrium, the global torque that acts on the system and the magnetization of the system will not vanish. And so what we can do then is extracting the anisotropy energy uh, from the torque. Now, more details um, on the approach can be found uh, in this paper, which you can also find a link for on the Vampire website in the support section. So how does this Monte Carlo work? Well, the Monte Carlo, this constraint Monte Carlo said works in two spins. These two spins will be picked randomly within the system, and they don't have to be neighbors. Also, just clarification, the approach assumes that the directions along which we constrain the magnetization is always along Z, and this is not a problem because by application of a global rotation we can always end up in this condition. So okay, let's go through these steps. So we select two spins, spin I and spin J, and the spin J we will also refer to as a compensation spin, and we'll see in a second why we call it in this way. So the first thing we do now is to apply a Monte Carlo wave to the first spin. So as usual, we perturbate the system, doing something. In our case, can be spin flip or random movement around the Unitarian sphere or around the cone, which will depend, whose amplitude will depend on temperature. Now we do this move. So this is step like Monte Carlo already described in the previous tutorials. Now what we will do though is to move the second spin, to actually adjust the second spin so that it will preserve the condition that the magnetization must be aligned along Z, which means at the same time that the mx and my component of magnetization must be 0. So we can see here then the condition for the new component of the spin J, of our compensation spin, which have the oppose the new directions of the spin I in the x and y. We do so, and then what we'll do is to determine the new component of the spin J along Z, which will have to have the same sign initially, and also we have this condition here, so this root square must be, this argument must be positive. If that's not the case, we will reject the move. So we will see there are steps, and every time if a step doesn't satisfy the condition, we will go back to the beginning where we need to again select two spins within the system. So then, assuming that the previous step was okay, we will calculate the new global magnetization along Z. And again, we have the constraint that the direction must be positive along the Z-axis. If this is not the case, we will reject the move. Again, just to point out that what we need to do in this case is just to account for the new spin directions. All the rest of the system has been untouched during this move. If mz, the new mz is positive, we will go and evaluate the energy change due to this this change in the spin I and spin J. So we calculate the change in spin I, which is the new energy minus the old energy, as in the usual Monte Carlo approach, and then we sum the two contributions. And what we will do, then we will compute this acceptance probability, P, or if you want, probability of being rejected is 1 minus P, which has the usual Boltzmann probability density factor, so this exponential of minus the delta change, the change in the energy due to the move on spin I and spin J, divided by kBT, which is the thermal energy, which will make that low temperature, the acceptance rates will be lower than high temperature. And this Breuil factor here is a geometrical factor, um, which needs to be introduced due to the fact that we are now dealing with two spins and the phase space slightly modified. Again, this paper contains actually all the details with appendices which go through all these steps. So when we do this, and finally we assume we have done our moves, we will have in the end we'll be able to obtain the torque. So now we will see, and then the free energy. And so in this case though, the energy of the system, because each simulation is supposed to work every time it's going at constant temperature, and because we don't have any variation in the lattice, as well as a constant volume, the energy of the system is given by the Helmholtz free energy, which has the internal energy and a contribution due to the entropy. Now, I will mention this again later, but we will see that usually this contribution due to the entropy can be neglected. Also though, in Vampire, what we don't do is to obtain directly F, the energy, but rather we will obtain the torque, and from the torque we will reconstruct the energy and the anisotropy energy density, which will be difference in energy between different directions. So here, this delta F, which ideally will be our anisotropy energy, can be expressed as function of the work. Actually, it's an integral of the work between path A and along the path point A and B for a reversible system, as it is for our case. And if we have a magnetic system, the work is the torque that acts on the system. If we think about a bar magnet and we apply a field, then we will have the torque that will make it rotate. And if we use this definition, then we can actually re-express the free energy as the integral, the variation in the free energy as the integral of the torque over the angular distribution, where now A and B will be two angles between which we vary and we constrain our magnetization. How do we calculate the torque? We do, in this case, atomistic systems. So the torque is actually the sum of over the torque that acts on each single spin, which is this sum over I over Ti, and the torque that acts on each single spin is the cross product between the effective field and the spin I, where the effective field, which comes from the Hamiltonian, will have all the contributions to the internal energy, which can be exchange, anisotropy, an external field, and so on. And the internal and the thermodynamical average of the internal torque, which is what we have here, will be will give us the magnitude of the total torque. Again, this you can find a demonstration of this, the proof of this, in the paper over the review paper of the Monte Carlo approach, constrained Monte Carlo approach. So this is what we will, the results that we will actually obtain running Vampire will be the torque. So the only thing that we are left to be done by ourselves is the then integration over the angular distribution. But let's see a few examples of systems. Um, let's consider the first case, and this is the simplest of the cases that we can think of. It's a uniaxial anisotropy system, which means the magnetization aligns preferentially along a single axis, which you can call the easy axis, and the internal energy of the system will be then following a sine square relationship where this Ku factor in front of it will be our anisotropy energy. And strictly speaking, at 0 Kelvin, the torque, which is can be calculated as the derivative of the free energy with respect to theta, and the free energies, we remember, as just said, is u minus ts. Now t is 0, so we obtain the sine of 2 theta relationship. Again, as I said before, usually the entropy contribution is not large, and it is possible to use these analytic relationships even at fairly high temperatures, accounting for the fact that as the temperature increases, the anisotropy will decrease, and it will anyway be more complicated to extract it. So the accuracy of the results usually will be slightly lower as we approach DC. So if we have a uniaxial system, then what we can have as a result? Well, if we run the simulation with Vampire, now here on the left, we see a graph where we have the angular distribution, or actually dependence on the internal torque, where we can see this is a uniaxial system, so the torque follows the minus sine of 2 theta relationship, and we just see 1/2 of the curve. So I calculated just from 90 degrees to 180, so to pi over 2 to pi, and this is done for different temperatures, and the results are normalized by the maximum torque at 0 Kelvin. So we see that the maximum here reaches 1, and it decreases as we increase the temperature. And if we integrate this curve from 90 to 180 degrees, we can reconstruct the angular dependence of the free energy for different temperatures. Again, we can see we have this sine squared behavior. It decreases with temperature, and well, it's just 1/2 of the curve again. This gives you the energy value substantially, which, because the main contribution here is the anisotropy, then, or actually in this case it's just the anisotropy, if we calculate the difference in energy between the maximum and the minimum, we will extract the anisotropy energy. Now, because in this case the maximum corresponds, because of it, we know how to actually the analytic expression. In this case, we can use a quadrature approach and extract directly the torque, from the maximum of the torque, the anisotropy, because this will be the integral. But for more complex cases, unfortunately, this is not possible, and we will have to perform the integration. Now, in the following, I will show you some how to run a simple system with Vampire, but I will not show how to perform the integration. These I leave it to you. There are tools in case that can be used, uh, Python or other softwares such as MATLAB, Mathematica, or you can write your own code to do it. So, as mentioned though, we do this for different temperatures, and what we can obtain is the temperature dependence of the anisotropy energy. So here on the left, we can see the temperature dependence of both the anisotropy and at the same time also the magnetization temperature dependence. They both normalize to the 0 Kelvin value. So the maximum is at 1. The reason why the magnetization doesn't goes to 0 is because the simulation was done for a fairly small system, so we do have some finite size effect, which will give you this deal. But the interesting thing then, if you do this, is that you can extract the scaling between the anisotropy and the magnetization. So on the right hand side, you can see the graph where I plot the logarithm of the anisotropy normalized by the 0 Kelvin value with respect to the logarithm of the magnetization, again normalized by the 0 Kelvin value. And what you can do is then obtain linear, well, a relationship which then you can fit, and this will give you ideally an exponent between which relates the temperature dependence of the anisotropy with that of the magnetization. And for example, you can then compare with what the Coulomb-Coulomb theory predicts. But again, not necessarily these comparisons can be applicable if you deal with some particular system, but it can always be of interest to understand how the two relates in a system. And this is something that you can do running the constrained Monte Carlo simulations. And just then as an example, here I show the scaling where I have not only the magnetization as before and the uniaxial anisotropy, but also the scaling with temperature of a system which has a cubic anisotropy. Now, this doesn't affect the magnetization because the magnetization temperature dependence, where we're looking at the length of the magnetization, will depend on the exchange and not on the anisotropy. So you can have the same temperature dependence of magnetization and different anisotropy for different systems. But the point is you can extract, and for example, what you would obtain is that the cubic anisotropy dies very quickly with temperature. So again, for applications, understanding how these properties are is very important. But how do we do this in Vampire? Here I will just point out the main parameters that you need to include in the input files for a constrained Monte Carlo simulation. For this case, there is no need to include any specific parameter in the material file, but we do need to include some parameter in the input file. And those are, assuming we do this now for a specific temperature, are the information regarding the constraining angle. So we have the polar angle, theta, and the azimuthal angle phi. And we can give you the minimum and maximum with which we want to run the simulation and the increment for both. Worth mentioning that the increment must be different from 0 even if we don't want to actually vary the angle, because otherwise we will incur a division by 0 within the code and problem will arise. Then we have the other important bit, which is we need to tell the code that we want to run a constrained Monte Carlo simulations where we use the constrained Monte Carlo integrator. So we say simulation integrator and then we say constrained Monte Carlo. And the program, so the type of simulation, is CMC-anisotropy, which is a simulation that allows you to um, vary the temperature, and also, as shown here in the parameters, vary the um, constraint angle, both the polar and azimuthal one. And then in the output, specifically for this case, we want to output, or usually we want to output the constraint angle theta, the constraint angle phi, the mean total torque, and it can be useful anyway to usually have the magnetization length. So I will now show on the terminal how to actually do this. So we go here on the terminal. First thing we do is we clone the vampire wireshark directory on our terminal. So we do git clone, we do the link, which is https github.com rigid events vampireworkshop.git. As we can see, it's cloning the objects and is cloning this in the directory vampire-workshop.git. Unlikely my connection is not very fast, and so it takes quite a while. So now what I will do is to go in the Vampire Workshop directory, and here you will find the slides, but also input files for tutorials and examples that can be useful and that we will use now. So I will go in the input files directory, I will go in the directory 2, constraint Monte Carlo and dipole fields, and then I will go in the cd in the 2 uniaxial case. So first thing that we need is to actually copy the executable file for Vampire to run it. So we go in Vampire serial, and I will copy it here. So we'll see we have this now. Let's go through the input parameters. So the input parameters have already been described before. I'm just going to go very quickly through. We set a BCC crystal structure. It's a full system, which means we're going to create a box. And we also set periodic boundary condition in the X, Y, and Z, which means we'll replicate this box in all the 3 directions to try to obtain property closer to a bulk system. We have the unit cell size and the dimensions of our box that we were going to replicate. Then we give the name of the material file, and then we will look at the simulations attributes. So instead, the constraint Monte Carlo simulation we want to run allows you to actually also vary the temperature. Now, for the sake of this tutorial, for speed reasons, I would suggest to reduce this range from 0 to 600, and we can leave the increment of 100 Kelvin. The Curie temperature of the material we will simulate, which is a cobalt, is about 1300 Kelvin, so it might take a while to do the whole range, and it's not important in order to learn how this works. Then we have these 2 parameters that you already have seen in the previous tutorials, which are the equilibration time steps and loop time steps. Now, the equilibration time steps in the number of steps, the code will integrate the system, and then they will be discarded. And afterwards, we will run again the integration for the loop time steps. And at the end of these steps, you will extract your property. In our case, we will want to see the torque. And the statistics will be calculated over these loop time steps, number of steps. Then we have, as said, the constraint angles parameters. So we don't want to run over the polar angle because the system is uniaxial, so it's supposed to be symmetric, and so there's no need. We can use the the theta equals 0. And we will vary the azimuthal angle between 0 and 90 degrees, and again, for the sake of this tutorial, rather than doing every 15, we will do every 22.5 degrees, which allows us to reach the 45 degrees where we expect to reach the maximum. But usually, if you have a system which doesn't exhibit what the usual properties are, then you might want to actually have a much finer angular distribution in order then to properly integrate the torque curve. And here you have the checkpoint settings, which we will not use here, so we'll comment out. The first one, the save checkpoint, if it is uncommented, can be either continuous or end, so it means save these checkpoint files throughout the simulation just at the end, and if it is continuous, you can give the second parameter, which is the rate. And in case you want to reload the simulation, you can use the load checkpoint flag with either continue to continue simulation or restart in case you wanted to restart the simulation from that point. And then we have the integrator, which is the constraint Monte Carlo, and the program, which is CMC anisotropy, which already described. And finally, we have the output. Now, with respect to before, I've also added the temperature output because I will increase the temperature throughout the simulations, and I want to know every point to what temperature corresponds. And we will also print on the screen, so if we do the flag output, this will output only on the output file, but instead we will want to see this on the screen. Again, usually you don't output on the screen if you run on a cluster, because it will just make it slower and it will output in some stream file, but if you run a test, or in this case, can be useful just to see what the simulation is outputting. And I'm outputting exactly the same thing. So then we have our files, and very quickly we're just going to go for the material file, which says that we have one material whose name is we set to be uniaxial. We said dumping 1, although this is not going to be used in the constraint Monte Carlo or Monte Carlo approaches. We have the exchange, which will determine our Curie temperature, and then atomic spin moment. What is interesting looking at the anisotropy, again, we want to run a uniaxial anisotropy system. So we have a uniaxial anisotropy constant, which sets the anisotropy to be along the z direction. We set the name, the element cobalt, which can be used when we render the configuration file with programs such as Rasmol, and then we set the simulations to have just the whole space occupied by the system, and we initialize the spin to be along that. So then what we will do is to run the simulation. So we have our vampire serial, and we will run the simulation. So the simulation starts. It says I've used the LLVM flag because I'm using a Mac. So what I will do now, because the simulations will take just about 20 minutes, I will stop the recording here, and I will continue when we're reaching the end to show the output file and how to look at the data. So now the simulation is finished, and we can see simulation ended gracefully. It tells you the time, in seconds, which is just about like 20 minutes. And it gives you some statistics about the Monte Carlo simulation. It tells you the number of moves, and it tells you how many have been accepted and how many have been rejected. Well, the energy sphere, are respect to the case where the move is a random displacement of the spin around the unit sphere, and energy instead with respect to the cone. With a cone whose amplitude which depend um, on the temperature. In this case, for example, hasn't been very effective, but also worth mentioning that the parameters were not perfect. So okay, we have done this. So we will want to look now at the output. So we can look at the output file, for example, and we can see, well, except initial comments, then it will tell us temperature as in the screen, on the screen, temperature, then theta angle, which we have kept 0, phi angle, so for each temperature 0, then we went to 25, 22.5 and so on, and then we have magnetization length for each temperature where we don't expect big variation due to the angle because it's a coherent system. And then we have the torque. Now the torque, because of the geometry and how the constraint is applied always along z, then the torque will be always along the y direction, while the x and y will be just noise. So we will be looking at this component here, in this case the sixth column of our simulation, and we can see we end up until 90 degrees. So what then we want to do is to plot the torque. So I will not show how to integrate, but I will tell you, as I already mentioned, we can extract it for uniaxial case from the torque, from the maximum of the torque at 45 degrees. Also, we'll show a few commands on uplot, which is a very powerful tool to plot. You can have it on Linux, Mac systems, and Windows if they have Bash, or also previous version you could install it somehow. With the uplot you can use conditional statements, and you can also use some Bash commands to edit, or let's say to play with your files. For example, in our case, because uplot, in order to plot a line, needs to have contiguous points, we will sort the data to have first all to sort by temperature, so all 0 Kelvin, and then with the angle that varies, and so on, so that you can we can plot, as I showed you before, the temperature, the angular dependence of the torque for different temperatures. So we will say that we want to plot, the file is output. As I said, we have now our output file here. And just to mention, we have the log file. If we go towards the end, says here we can see initialize the spins a new direction, and every time you change the angles, it will tell you in the log file. And again, it reports the statistics in here. So we can now plot. So as said, what we want to do is to sort the data. So we use the syntax where between quotes we will have the output file, but we also give this command, which is minor sign sort. Minus serves to indicate that we use a bash command, and we say minus k, which is stay for key, and say to sort by column 1g, column 1, and we say column is a number, so g, and then we say which is the temperature, and then minus key 3G, which is the phi angle, and then we say the output file, we close quote, and then we say to plot using column 3 and column 6, which is the angle phi and the y component of the torque. Now, if we do these, we'll see numerous points, and this will all for the temperatures. We want to do actually is to plot these for different temperatures. So what we'll do is to say plot. We want to plot column 3, but let's say we want to do this for 0 Kelvin, so we will use conditional statement. With $, we will signal to, will indicate we are considering a column, so we do column 1, if column 1 is equal to 0, in this case 0 Kelvin. With a question mark we indicate what happens in the case this is true, and we say if this is true we would like new plot to plot column 3. And in case this is not true, which you indicate with a column, we will give a new plot a statement which cannot be interpreted. In this case 0 over 0, this cannot be plotted. And then we will give the new column, well, the y axis to be plotted, which is again column 6. And then we will specify to plot with line points where W stands for width, LP stands for line points. You can find all the documentation of NewPlot on their page, and in general on the web. It's very well documented, and you will find all the information you will need. And then we can say T, the stands for title, and we can say that we plot this 0 Kelvin. So now we go back to our plot, and we see this is our torque. So on the X we have the angles, phi, and the torque, which goes as a minus sine of t of theta, which is the expression here, and this is what we have. And then we can do the same for a different temperature. So we'll plot same file. This time we will ask though for a 300 Kelvin, for example. And then we will say if this is true to plot another line. So this will be 300 Kelvin, and what we expect to see is a decrease in the torque. And now, as I mentioned before, because we know which is the analytic expression in this case, we know that the maximum of the torque, which is a 45 degrees, will also gives us the maximum in the energy barrier, and therefore we can in this case avoid to perform the integration, and we can extract the torque from here. For more complex or in general complex cases, or in general, there would be better at least to make sure that the system follows the expected trend, and in case to doesn't to integrate, so we will need definitely more points. But this is just to show what we can obtain and how we can actually plot it. So we can see the output file has all the information we need in case we just need to post-process the data. So I showed these, and then if I go back to the slides, if we would run simulations with every 15 degrees, for example, in this case, with more temperatures, this is what we actually would obtain. So our torque is a function of angle, and then what I did was to perform a fit. These lines are a fit, which you can actually do in NewPlot, but you could use whatever other software you prefer, Origin, for example, and these are sine of 2 theta expressions. And then if you would integrate or extract directly the torque, from the torque the the anisotropy energy density in this case, then we could, for example, plot something like this. This is the initial tutorial. The next will mainly be hands-on and to show how to set, for example, other type of anisotropies, and also to deal with more sophisticated part of the constraint Monte Carlo, such as the hybrid constraint Monte Carlo.